Hey everybody, trying this again. QuickTime's being weird. So let's get this right this time. Okay, so we're going to talk about naive Bayes today. Um, so we've talked about classification. It lies at the heart of both human and machine intelligence. Deciding what letter, word, or image has been presented to our senses, recognizing faces, sorting mail. These are all things we do every day. So we're going to talk about and we've talked about many algorithms to do this: decision trees, support vector machines, feed-forward neural networks. Today we're going to talk about naive Bayes algorithms. We're going to talk about it in relation to categorizing text, but you can use naive Bayes to categorize anything, images, sounds, anything that you can have some kind of distinct feature for. Okay. So what we're going to do is we're going to pretend we have a text document. It's going to be represented as a bag of words. So a lot of times when we think about text, we think, well, each word has to do with the other, right? Like adjectives and nouns, right? Like small dog, right? So small describes the dog. But to represent, if we wanted, that's called bigrams, 2 words at a time. If we wanted to represent that at features, that's going to be a lot of features. So instead, what we end up doing is just treating each word like it's an independent feature, like it has nothing to do with the words around it. This isn't really true, but it's usually good enough to do text classification, this assumption of independence, to do text classification really well. And it's really, if we assume there's independence of our words or features, we can use naive Bayes. So, here we have this text about a movie review, and then it's like we took all the words, we like kind of, shook them all up here, and then now we have our word frequency, and that's all we care about. Okay, so basically this is our naive Bayes algorithm we're going to use, or equation. I'm going to show you how it's used with an example, but right now I'll just explain it. So the idea is we're going to have, let's say it's movie reviews. So we're going to have negative movie reviews and positive. And let's say we want to classify a new review as positive or negative. So this is the probability of just a negative or positive training example. And then this for each class, this is the probability that our word appears in the class. And here they multiply these probabilities together and then multiply by the probability of the class. Multiplication of these probabilities will often be pretty small, is going to make us have a really tiny number. And that number will usually, if we have enough words, will underflow our computer calculation, or it's basically going to do too many digits for our computer to represent, so in memory. So to get around that, we use a summation. And so neat little trick here is if you take the log of a probability and add it together, you're basically just kind of normalizing these features to all be on the same scale, log scale. And then since we're taking the log here, so if we take the log, then we have to do summation instead of probability. And then here we're just taking the log of this probability of the class. Since we're doing that here, we want everything to be on the same scale. And then, just one second. I'm setting up something on my computer. Okay, so if we take, this is just showing what this looks like in terms of words. So we're basically saying here that the probability of a word based on a class is going to be, originally it was, when they first started doing naive Bayes, it was just the count of a word in a class divided by the number of complete words for that class. This is the probability. But what happens is some words are not in that class, and so we'd get a 0. And then those zeros, when we were doing multiplication, would like zero out the whole thing and kind of mess us up. So they added a 1 to it, and that's what we're doing there. And then here, if we add a 1 to each count for every word, this is basically the same as, basically they took this 1 out and just made it the number of words, because it's the same thing, number of words in the whole, in the number of distinct words, basically. It's called the vocabulary. We'll see an example, and then we just have that plus 1. But so this is what we're going to use in our example that we're doing next. Okay, so let's look at this, and it'll make everything make more sense. Okay, so let's say we have this training data. Here's some sentences that are movie reviews, small movie reviews. And then we have this new example of a review that we want to see if it's positive or negative. So let's see the probability that it's positive and the probability that it's negative. Okay, so first let's find our class probabilities. Remember, that's the thing. Let me go back here that we need to find. In this example, they don't take the log because it's such a small number of words that we're not going to have underflow. So we'll just use this. If you have a homework or a test, I'll tell you what to do there. So don't worry about that. You have to remember. Okay, so here they're going to have the probability of a class being negative. Well, it's 3 of the 5 examples. And the probability of not a class, but the probability of an example being negative. And then here's the probability of a example being positive. So it's 2 out of 5. So we'll find that. And then for each word in our training example, we're going to find the probability, our test example, we're going to find the probability of that word being positive or negative for each of the words. Okay, and then we'll see here, we'll finish up. So the probability that predictable is negative. Okay, it occurs once, and then we're going to put the +1. Remember, we're doing that for all of them. See all the +1s to keep for when we have these zeros. That's not very good, right? And then here is going to be the number of words, and I'm pretty sure it's the number of words in total. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 14. So just the number of words. And then this is the number of words in the vocabulary. And what this means, see how these are all the same across positive and negative? It's the number of distinct words across all the examples. Distinct, okay? And so that's 20. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, looks like. Okay, and I just did a quick count there. Okay. Then so we have that, and then so we've done the probability of predictable being negative, probability of no being negative, probability of fun being negative. See, that was not in there, so we have the 0. Then probability of predictable being positive. This is going to be the number of words in the positive examples, 1, 2, 3, 4, 5, 6, 7, 8, 9, plus just the size of our vocabulary. So we have these here, probability of no being positive, probability of fun being positive. Then we're going to put everything together. Okay. Oh, and then here what they did is they said, and I would tell you this in homework or something, if I don't mention it, you just use it. With this, maybe a word they think doesn't give us much information, so they just didn't count it. So that's what they're doing there. If you're going to be here next year and you want to, and I end up teaching text mining, that's a class where we're really going to detail with what to do with text, and then, in this, like getting rid of the word with and all these fun things. We would be taught more detail there. But right here, we're just going to say, yeah, they just got rid of it. So probability, here we're going to find the probability that the test example is negative. So it's probability of negative class, which is 3 divided by 5, times the probability of all those words being in the test being negative. So we just remember we had these here. So they just added it together. So 2 times 1 divided by, that's 34. So 34 cubed. And we get this tiny number. See how close how tiny this is? Imagine if we had way more words. See, that would underflow. And in that case, we would just basically do the sum of these, and then the sum of the log, and then the log here, if we were worried about that. But we won't worry about that here. And then 2/5 for the test example being positive. We have 2/5 times 1 times 2 divided by 29 cubed. We get this number. So looks like it's more likely that the example is negative. If we read it with using our powerful human brain, we can tell that this is negative, right? But the nice thing with machine learning is then we don't want to have a person to sit here and figure all these out. We can automate this, right? That's how now we have fun things like Alexa. It's automated, right, with like voice prediction and stuff, because we can have these machine learning algorithms to do some prediction for us. Okay. Another thing they can do here, which doesn't really matter so much for our class, but we'll just talk about it. We don't have to use the word frequency of the count. We could just say if it's present or absent. That's just another strategy. We're not going to talk about that. I'm going to take that out. Another thing that's important is, so we want to evaluate, how well our machine learning method's doing. Let's say, you have something you want to use machine learning on, and you have deep learning, which we're going to talk about this week, and you have naive Bayes and support vector and FFnet, and you just want to try all the different things. You need a way to see, well, how well did each machine learning method do? And that's what we're going to talk about now. So to introduce the methods for evaluating text classification or any kind of classification, let's consider some simple binary detection tasks. For example, in spam detection, our goal is to label every text as being in the spam category, positive, or in the not spam category, negative. For each item, our email document, we therefore need to know whether our system called it spam or not. We also need to know whether the email is actually spam or not. In other words, the human-defined labels for each document that we are trying to gold label match. We will therefore refer to these human labels as gold labels. Okay, so let's look at this. So you probably heard about this with like, clinical tests. Like right now it's COVID. Maybe they're talking about how well these antibody tests are doing, right? And so these are the different ways to think about how a test does. So what we want is the screen, okay? So basically we have, this is what it should be, and this is what our system actually predicted. So let's say, let's do our antibody test, okay? So let's say the person actually had COVID, and then our little test strip said that they had it. Then that's great, right? Let's say the person doesn't have it, and our system says they don't. That's also great. Now other things that can happen. Let's say the person doesn't have it, and the system says they do. They've had it. Well, that's really bad, right? Let's say with COVID, that's bad because now they're going out and thinking they're immune when they're not immune. Okay, let's go here. Here the person had it, and the system says they didn't. In this case, the person now is like kind of doing all these extra precautions when they have immunity. So this is kind of what we're not, what we're aiming for. But depending on your system or what you're trying to do, like with COVID, of course, it's serious. So both these are equally bad, maybe. Maybe this is worse because they're going out more. But, sometimes this is okay and this isn't, it just depends on what you're kind of looking for. But what we're going to do is kind of balance out all of these different ways our answers can be right or wrong, okay? And so we're going to basically use precision, which is the true positive divided by true positive plus false positive, and then the recall, which is the true positive divided by true positive plus false negative. And we have accuracy, and that can have some issues. We're going to talk about why we're not going to use accuracy, okay? So although accuracy might seem a natural metric, we generally don't use it. That's because accuracy doesn't work well when the classes are unbalanced, okay? So why accuracy might not be great to use. Imagine we looked at 1,000,000 tweets and only 100 of them are discussing their love or hatred for a pie. Let's say we're a company that makes pie. While the other, vast majority of tweets are about something completely unrelated to pie. Imagine a simple classifier that stupidly classified every tweet as not about pie. This classifier would have a lot of true negatives and only 100 false negatives for an accuracy of 99.99%. And that's an amazing accuracy level. But is our system doing what we want it to do? No. So that's why we don't use accuracy. We're going to use precision and recall. Now, instead of having to basically report precision and recall, which we can totally do, and most people do, like in a paper, they'll say our precision was this and the recall was, this other thing. We can combine those scores together and just get one score between basically 0 and 100. And usually in papers and stuff, what we want is something above around 87 or 88%. That's kind of just what you usually see. So there are many ways to define a single metric that incorporates aspects of the precision and recall. This simplest way is called the F measure. It's basically 2 times precision times recall, and then precision divided by precision plus recall. So that is naive Bayes and precision and recall and F measure. You have a homework I put up there. You have a few questions about this. If you have any, questions, please email me. I'm going to have time online throughout this week. So, yeah. Okay. Take care. Stay healthy.